Hi everybody, we got a circuit today with two questions. Let's draw the circuit first. A voltage source with a sine wave, 60 Hz, 120 volts. Just be in mind, this is already RMS, effective voltage, which has a parallel circuit with a resistor and an inductor, and parallel to this is a capacitor. Let's call it RLC. And the questions we got is, what is the function for the current depending on the time? And the other question is, the voltage is at 60 degrees. What is temporary value of the current? Okay. First remark, when we see this, you see already this is a series of a resistor and an inductor. What is it? It's real life scenario. This is an electrical motor. The motor has an inductivity and a resistance, and it's compensated by a capacitor for the power factor. We don't talk about power factor today, but just to be in mind, the capacitor is there in order to compensate the reactance of the inductor. Okay, how to solve this? We have two different ways to solve this. Ohm's law says the current is the voltage divided by the resistance, in this case the impedance. If we calculate the impedance, we can figure out what is our current. The other option is Kirchhoff's law. Kirchhoff's law, which says that the entire current is actually the sum of all currents in the circuit. We have here this current going through the series resistance of the resistor and the inductivity, and here the current going through the capacitor. The easier way to calculate is actually going this option, because it makes it a little bit easier, because on this one, when we go via the impedance, it ends up in calculating the parallel impedance. In case of two components, it ends up in a pretty complex mass, ZRL times Z von C divided by the sum ZRL plus ZC. Here you need complex mass, so that this one is actually easier. We are going through the circuit, through the currents. The benefit is, if you find the current already, the sum, you have already our solution. We end up in this one. E von t is actually the magnitude of the sum current multiplied by the sine of omega t plus the angle phi, where the phi comes actually from the phase shift of I, our current. And then when we want to solve the other equation, what is I at 60 degrees of the voltage, we can say, okay, this is just this formula, but the phase angle is actually the difference between the voltage and the current, and then we can calculate the temporary value of the current. Okay, so far so good. Let's go with Kirchhoff's law, approach number B. Don't need this one. Don't need this one. Okay. First of all, we have to calculate the impedance of the series resistance, ZRL, which is nothing else, just the resistor itself, plus J omega XL. XL is omega L. The reactance or the impedance of the capacitor is 0 plus 1 divided by omega C. Bear in mind, this is at 90 degrees, and the XL is actually at minus 90 degrees. That means the current on an inductor leads the voltage by 90 degrees. On the capacitor, on an inductor it lags by 90 degrees, and on the capacitor it leads by 90 degrees. We have to bear this in mind a little bit later, just to cross check is everything okay. If we calculate all this stuff, then we use again Ohm's law. The current through the RL branch is nothing else than the voltage of our power supply, which is a vector, divided by the impedance of our series resistance. The current through the capacitor is the same, not the same, similar, divided by the impedance of the capacitor. And at the end we can do E, let's say the total E is nothing else than the sum of both. I see. We can do this in a vector diagram or in a phasor diagram. This would be the current. This is our real part. We have the current through capacitor, AC, which leads the voltage. Then we have the current through the resistor and inductivity part, which is maybe this one. it's IRL, and then at the end we get a resulting vector. This is E total. We will see here that this angle is 62 degrees, this is 90 degrees, and the resultant vector is minus 9. Actually, there is also minus 9.45 degrees. We get a magnitude for all these vectors. So that we have at the end we have I of t is actually our magnitude, our sound current we have calculated. We have a sine wave, omega t, plus the phase vector, which comes from the vector of the current. When we would draw this, we would see this, let's say this is our voltage, and the current lags a little bit, like, sorry, the current lags by minus 9.45 degrees. If we want to know the current at 60 degrees, this is pi, this is pi halbe, 60 degrees is P divided by 3. Here's our voltage on 60 degree. We want to figure out what is the voltage on this point. We bear in mind that the phase angle is important. That means this one is -60 minus our 9.45 degrees, and then we can calculate, and then we get our temporary current at 60 degrees. Okay, so far so good. What we can realize later when we talk about power factors and all this stuff, this capacitor here is there in order to compensate the reactance of the inductor. We have 50 microfarads, which is pretty good, which gives us a power factor of roughly, which is cosinus phi. Our phi is minus 9.45, and then when we want to optimize to 1, actually this one should have a value of 54.82 microfarads. Then our power factor would be optimal. We don't waste any power, and everything, even the current and the voltage, get in sync with each other, which is always the goal. when it comes to electrical motors. Okay, thank you.